Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it's an honor and a privilege to be serving you here today, as it is every day, here in my virtual classroom. Step on inside as we jump into section 2.2 in the Big Ideas Math Integrated Math 3 textbook on transformations of linear and absolute value functions. Now, we started section 2.1 of transformations of parent functions, going from the parent function to something where we had constant, barely constant, but constant, linear, absolute value, and quadratic. Now we're focusing on just linear and absolute value functions themselves. We should know how to graph them from previous bits, whether it was section 2.1 or whether it was IM2. If you need to use a table, I suppose go ahead. We'll see how often we have to graph these ones, but they're talking about the transformations themselves, how the different parameters in the function affects different parts of the graph. So we'll see what we do. Jump on the description section down below and download this PDF if you'd like to and follow along with what I'm going to do, timestamp and lecture and problem set. Find the timestamp corresponding to what you want to find with me here. Without further ado, I'm going to go ahead and get started. Let's go ahead and no new vocab. That actually stands right out to me. What you'll learn, you will learn how to write functions representing translations and reflections, write functions representing stretches and shrinks, write functions representing combinations of transformations. So combinations is all of them combined, translations, reflections, stretches, and shrinks. Notice that first of all, they say write functions. That means make the equation. But notice that they do not specifically say vertical stretches and shrinks. It's possible we are going to be diving into horizontal stretches and horizontal shrinks here. And I might be showing you at times how to make them into vertical ones as well, because I kind of like them more, but we'll see. Depending on what they do, depending on how they teach it. Okay, now we started talking about this stuff in section 2.1, so this might seem redundant to you, and if it is, keep moving on. Translations and reflections. You can use function notation to represent transformations of graphs and functions. Very true. Let's see what they want to talk about. Horizontal and vertical translations are based off what you see in here. Now, the graph, notice this y equals f of x right here, yeah? What if you take it and turn it into y equals f of x minus h? The minus h inside the function portion is something that will horizontally translate your original graph y equals f of x. Where h doesn't equal 0. Otherwise, there's no translation if h is 0. But if h is 1, if h is negative 2, if h is pi, if h is 7.4, then you start to see some horizontal translations of your graph. Now, notice it does say x minus h. I don't know if they're going to be talking deeply. Well, let's see what this says. Subtracting h from the inputs before evaluating the function shifts the graph left when h is less than 0 and right when h is greater than 0. It's a very technical way of stating that, yeah, when h is a positive number, you'll see a minus in here. You have to flip the sign to see which way you go. And you're probably familiar with this. When it says x minus 2 inside of there, you go 2 to the right. The reason is, and they're saying it right here, before evaluating the function, the inputs before evaluating the function. You are plugging in an x value that's opposite of what your h value is, the thing that would get you 0. Is the thing that goes there. So when x is h, y is 0. That's the whole bread and butter of that. So that's the horizontal translation, h units left, h units right, etc. Vertical translations is something that's outside of the function itself. It's what affects your output. Adding k to the outputs shifts the graph down when k is less than 0 and up when k is greater than 0. So your original function is here. And let's do this, take this function and add k to it. Now keep in mind, all this stuff with functions probably looks very strange to you. It says this f of x stuff. You're like, what are we doing with that? A function can be anything. It can be linear. It can be absolute value. That's what we're going to focus on here. So that f of x can say negative 2x plus 7. It can say 1/2 times absolute value of x plus 3 and then minus 5. It can say whatever it is, but then we're going to do something to it. So that doesn't really sound like we're going to do much on graphs yet. We'll see what examples they have, because it doesn't seem like it's going to be graphy just yet. So let's look at this first example. Let f of x equals 2x plus 1, which is a linear function, by the way. Write a function g whose graph is a translation 3 units down on the graph of f, and then do a translation 2 units to the left of the graph of f. So we just heard what translations do here. When we go up or down, that's where we add or subtract an amount to our function. Remember, our function is this. But what we're going to do is take our function and we're going to go 3 units down. That means we're going to subtract 3 to our function. So we're going to take whatever the function is and, well, they say add. We're going to add negative 3. We're going to subtract 3. So we're going to take the function. Here it is, 2x plus 1. They're substituting that for f of x. And we're going to do 2x plus 1 minus 3. So you combine like terms. What's 1 minus 3? It's negative 2. And here's the new equation, g of x, 2x minus 2. It's simplified. But this graph should be 3 units lower than the original function that we're looking at here of 2x plus 1. I know I'm just circling things right now. I know it doesn't mean much, but as I talk about it, I hope it does. Oh, here's their graph right here. The original, oh, this is, I only did part A so far, by the way. Part A, G compared to F. Here's F, here's G. What's the difference? It's translated 3 units down. Take a look at where it was. Take a look at where it is now. That's 3 units down from where it was before. And that's not just the y-intercept. That's any point. This is 3 units down from here, etc. So what did it take? It took taking your original function and subtracting 3 from it. We wrote a different version of it, and you can graph it using slope-intercept form. You can graph it by translating it 3 units down, but the fact of the matter is those are synonymous with each other. Now, part B is translating 2 units to the left of the graph of f, and this is where you got to be a little careful. Now, what they do first is probably something I'm going to be doing as well. Maybe skipping the first step as a whole, but it says x minus h, and our h is -2. We're going 2 units left, so we got to subtract -2. Subtracting a negative means adding. So what does f of x plus 2 mean? If you know anything about function notation, it means you substitute this into your input, or this is your new input for your variable. Where your original equation said f of x equals 2x plus 1, x is your input. So what goes into your input? X plus 2. So instead of saying 2x plus 1, it says 2 times x plus 2 plus 1. That's what's taking its place. Now, this input is affecting your overall equation, and it's doing it in such a way that it's going to translate your graph 2 units to the left. The simplified version of this, of course, is you distribute 2 into these. You get 2x plus 4 plus 1, and 4 plus 1 is 5, and you get 2x plus 5. So this is the new equation of that. If you see this graph, 5 is the y-intercept. It goes down to left 1, apparently, to fit it in this window. And that's the same thing as taking this graph of f and translating it 2 units to the left. Now, you might be confused still, and I understand if you are, but part of it is understanding things regarding function notation. Understanding there's a flippage inside of here, and, you know, it's for a reason. I'll see if it's a reason I should be exploring here, depending on if we're talking about the graphs, if they're going to explore it. But, yeah, those are the 2 different things by substitution. Now, that is just specifically for translations. We're going to do some things, obviously, with stretches and shrinks. We're going to do things with reflections, probably coming up right now. Yeah, let's talk about reflections next. So there are 2 kinds of reflections, and we've seen reflections in the x-axis all the time. Reflections in the x-axis is when you change your y's from their positive counterpart to negative, or negative to positive. You change their sign. And what you're going to see is a negative on the outside of your function itself, specifically on the outside, because it affects your output. Reflecting in the x-axis means it's changing the y from negative to positive and vice versa. So the graph of y equals negative f of x, the opposite of f of x, there is what happens. So if your original function is whatever this is in black right here, flip it across the x-axis, and now it's this one in red right here. We're flipping across that. We've done a bunch of those. We did it in the last section. That's generally the ones that you see. Reflecting in the y-axis is a different story, though. Again, one that may perplex people. The ones that will confuse people most, I'm going to just admit right now, are the ones that affect your inputs, not the ones that affect your outputs, especially when you have to think very opposite of what you do. But with these ones, this is where your input changes sign, multiplying your input by -1. Okay, that's a reflection in the y-axis. Think about that. Reflection in the y-axis changes x. You wanted to plug in 2 for x? No. Now you got to plug in -2 for x to get the equivalent y value that you would have before. So this graph, this graph right here that's in black is now not flipping over the x-axis. It's flipping over the y-axis here. So it goes over this guy right here, and it becomes that red one like that. Will flipping over y and flipping over x sometimes be the same thing? Sometimes. Not always, very rarely. Depends on the symmetry with the origin and such. So, there's symmetry about those 2 lines of symmetry there's symmetry across those lines of reflection that we have. All right, let's take a look at some examples of what they do. Let's write a function g. So here's the original graph. It's an absolute value function, part of what we're going to do. Let's write a function g whose graph is the reflection in the x-axis, and then we'll do one whose the reflection in the y-axis. Now remember, f of x is this entire expression. You got to keep that in mind when it comes to these reflections. This is why, see, normally when we reflect, it's the first thing we do, but now we're taking this entire graph and flipping everything over. We're not just making the v shape go upside down. We're taking whatever vertex it was and putting it on the other side of the x-axis. We're flipping everything over, guys. So now you have to make sure you follow order of operations and what things do. But what they're going to do You say g of x is a reflection in the x-axis. It affects your output, so we're going to make the output the opposite of what it was. That doesn't mean make every sign negative, but it means make your whole function the opposite of what it was. So negative f of x is this entire thing. That's why they wrap it around parentheses with the negative. And then what do? They distribute the negative to each individual term or quantity in the expression to simplify it. So they distribute it to the absolute value, not into the absolute value. The absolute value is protecting your quantity. It's a PEMDAS thing. But it's distributing it to that to make the absolute value the negative, opposite of what it was before, positive, and it takes the plus 1 and it makes it negative as well. Now, I know there are things that you might get a little tricked out by as far as, oh, can we distribute the negative into here? Like I was saying, you cannot. You cannot. The absolute value very much protects what's inside of there, so you can't do that. But as far as simplifying this, getting it in a proper vertex form for absolute value graphs, this is the appearance of it here. Negative, absolute value, x plus 3 minus 1. And if you know anything about these graphs, you might have to use a graphing calculator. They have one showing right here, actually. We're just looking at G. Here's G in red compared to F. Here's F. Here's G when graphed. Now, all they did was input the equations. They didn't say, let's take this and flip it over. They said, let's take this equation, put it in the graphing calculator and see what comes out. And notice it's reflected across the x-axis. It didn't just flip the graph over from right side up to upside down. It changed everything. This vertex is now down here. It flipped over. So it did the reflecting last for that function. Now let's look at part B where we reflect in the y-axis. So in reflecting in the y-axis, what do? You make the input negative now, not the output. So instead of negative f of x, it's f of negative x. So remember what this does? This is your new input into your equation every time you see your variable. The original one just had the variable right here, x. So what do? Turn it into negative x. I say this all the time. It's almost jokingly, and I almost don't really smile at it anymore. If this said f of booger, then booger replaces x. It would say absolute value of booger plus 3. It doesn't matter what expression it is. It could be big, it could be small, it could be complex, it could be negative, it could be the same thing. It could be 2. Whatever it is replaces x. So what was before x is now a negative x. I want to stress that importance because it's one of the things people probably mess up most in function notation, even in IM3. Even if you've been doing function notation since IM1 the last couple years. Anyway, negative x plus 3 goes here. Now they do something really interesting, and it's something I admittedly would do too. I say that because I didn't expect them to do it, but here's what they do. And you might get lost. The first thing they do from this step to this step is they factor, it says right here, they factor out negative 1. The reason behind this for you is probably unclear, but when it comes to something known as vertex form for an absolute value function, you want this to just show an x. You don't want it to say negative x. For my things, you don't want it to say 2x or anything. You just want it to say x. There are a lot of reasons for it, and it has to do with your idea of what the actual vertex is and horizontal translations and things like that. That being said, when you factor out the negative, what happens to this plus 3 is it becomes a minus 3. Speaking of horizontal translations, you thought of translating 3 units to the left? No, you actually go 3 units to the right. But they do something even more so here. They don't really write this negative 1. They did say factor out negative 1. Remember, this is technically a negative 1 that's right there, right? This would have been a negative 1. This is a negative 1. Now, there's a property of absolute values that when you have an absolute value of a product, you can split it up into the product of 2 absolute values as such. And guess what? They do that. Now, why do they do that? Because negative 1 is a constant value, and you can simplify the absolute value of negative 1 into positive 1. You look at this thing and you say, hey, where did it go? Well, they're telling you. They simplified it. What's the absolute value of negative 1? Positive 1. What is 1 times anything? It's just that thing. So where's that 1? You don't need to write it. It's gone. So they simplified this. And again, I might have lost you in this phasing. The book's doing the same thing, though. But they're writing a version that is the equivalent to a proper vertex form. Whether or not you know, you should know vertex form from IM2, this x minus h plus k and that kind of stuff, and there'd be an a on the outside. They don't want a number in front of here for a lot of different reasons, how much it affects it. Apparently it didn't affect it very much, but it does show that this graph now goes 3 to the right. Remember, you flip the sign inside here. It goes 3 to the right for the vertex. It's at 3, 1, and here's that graph of h. By the way, compared to f, notice how it's a reflection across here. So they did properly reflect it over the y axis to get the proper graph there. Change the vertex and all that. So that doesn't mean that you understand everything fully in here. This is but one example. I'll try and make sure to explain more as we go and ask questions in the comment section if you have them. Welcome to the world of IM3. And like I said, not meaning it's hard, but we're taking our knowledge from IM2. The book expects you have knowledge from IM2. And we're taking that knowledge from IM2 and applying it to IM3 in such a way that we know how to factor, we know how absolute values work, we understand what vertex form looks like. And I didn't know if they expect you to know it or not. It seems like they kind of want you to know it. I think their check is with the graphing calculator for now. But the reflections of these things are as such. Oh, and function notation. And that you know function notation. You know how to substitute something in there. Whether it's a negative x, whether it's a number, whether it's booger, whatever it is, we can go on from there. Anyway, let's keep moving forward. Let's talk about stretches and shrinks. And notice, right, straight up, they talk about horizontal. I think I want to talk about vertical first. Let me not move myself. Let me start with vertical first, but let me first read this part. In the previous section, you learned that vertical stretches and shrinks transform graphs. You can also use horizontal stretches. Yes, you can. Horizontal will confuse the ever-loving everything out of you. To the point that I, Mr. Robinson, prefer to not that I don't prefer to talk about horizontal stretches, I prefer to make horizontal stretches and shrinks into vertical stretches and shrinks for every graph conceivable, for every function conceivable that I can. And I'll show you it in comparison, but if the book swears by horizontal stretches and shrinks, every so often we might have to talk about it, especially if your teachers go by it. Yeah, but this guy said this. I don't know how much you want to go off this guy for this kind of stuff. I'm going to be right, but we got to see what they say as well. Because here's the thing. We talk about horizontal translations, so I think horizontal stretches and shrinks maybe have to be a part of it. It's just that horizontal translations can't turn into vertical translations for every function that's not a linear. All right, let me skip horizontal for a moment. Let's go to vertical because we've seen them a little bit from the last section and previously. The graph of y equals a times f of x is a vertical stretch or shrink of y equals f of x. Now, a represents the vertical stretch factor parameter. That's the value. If a is 2, then it's a vertical stretch by a factor of 2. Everything's twice as tall. Things you would have known from the previous section or from IM2. When a is 1/2, it's a vertical compression or a shrink factor of 1/2. It's not just about slope, right? Not everything's a linear function or absolute value function. It could be quadratic, but everything's half the heights that they were before, or double the heights, or triple the heights. Now, a could be a negative number, but we already know that the negative has to do with the reflection portion. So even if it says -5, we don't say vertically stretched by a factor of -5. We say we reflected in the x-axis, and we vertically stretched by a factor of 5. So the negative is a part of a, but it's not the component that we're really focused on when we talk about stretches and shrinks. If a is -1, that's neither a stretch nor a shrink. That's only a reflection. Okay, so keep that in mind. Now, that's taking the output, right? The output is affected by a multiplying by f of x. Whatever f of x is, whether it's a number when you plug in a number for x, or whether it's the whole expression, you are multiplying your number a by that expression or that number, and it's affecting your output. That's why it's affecting y, not x. How do we affect x? When there's a parameter multiplying by x inside of the function. That's what horizontal stretches and shrinks are. Now, the place you have to be careful, and this is where I'm actually surprised. I thought they would have used a different letter B. I would have probably written that letter B inside of there. I might change them. I might change them up, but I'll write what they have for now. The graph of y equals f of, this isn't f times, this is f of a times x. Is a horizontal stretch or shrink by a factor of 1/a. Now, this is where it gets really confusing because you have to remember, and I might have to detour, I might have to digress a little bit right here. You have to remember that in these equations, let me write the whole kind of thing here. Let's talk about an absolute value one just for a moment, just to humor you. Like this, right? You might have seen this vertex form before. Remember where we say the vertex is at h, k, things like that. And we only see a vertical stretch factor right here, VSF. A is your vertical stretch factor. Now, the thing I wanted to first bring up was this negative here, this minus h. I did mention before that when something is inside the function, you have to flip it. You have to take the inverse of whatever you do. The inverse of subtraction is addition. You take this negative, you make it positive. The reason is because, and I know I might confuse you when I state it, but it is the reason. The reason is because We have to say, this number is affecting our input. So we have to choose an input that counters what this thing is doing for it. If this says x minus 2, we have to choose x's that are twice as big to counter the fact we're going to subtract 2 after. That's why when we choose an x of 2, it's 2 to the right. That's why we have to go to the right 2. It's not about it's technically not about taking this and changing its sign. It's about asking what value of x do you have to plug into here to make this 0. That's really what it is. Now I bring that up because now this a is inside of here, which I would have wanted to call b, but it's a. This a is inside of here. The question is, what value of x would you have to plug into here to counter and negate this a here and make it the inverse, the multiplicative inverse, to make it 1, not 0, but 1. The answer is 1 over a. If a is a number like 2, if this says f of 2x, whatever, or in here, if this says f of x equals absolute value of 2x plus 4, like that, and I'm sure we're going to get those. When it says something like this, well, there's a factoring thing that we're going to do, right? And that's why I like that they did that before, that you should factor the 2 out of here. But one of the questions regarding x is, what value of x do I have to substitute in here to negate this value right here, to make it opposite of what's going on? And the answer for that is 1/2. 1/2. 2 times 1/2, those cancel out, you get 1, right? It's a multiplicative inverse. So you want to do opposite of what's in there. They do the same thing by a factor of 1 over a. Case in point, as a gets bigger, it's not a horizontal stretch. It's a horizontal compression. When a is 2, you horizontally compress by a factor of 1/2. When a is 5, you horizontally compress by a factor of 1/5. When a is 1/3, you horizontally stretch by a factor of 3. When a is 1/10, you horizontally stretch by a factor of 10. Now I can get into it more if I talk about how it becomes a vertical stretch or compression if you do the same things that they did with the -1 on this previous problem, and I guarantee I will be doing it with you on problems. But we can also look at, we're talking about linear equations as well, right? We can also look at slope-intercept form, y equals mx plus b, and look at how a 1/2 as a slope is not only a vertical stretch factor of 1/2, but it can also be a horizontal vertical compression factor of 1/2, but it can also be a horizontal stretch factor of 2 when we look at them. So let's see what they do with those. And yes, this is going to be a long lecture. Writing stretches and shrinks of functions. Now let's hope that we do some vertical ones first, or I'm going to start with vertical ones. Let f of x equal this absolute value function here. So they're going to start with absolute value. Write a function of g whose graph is a horizontal shrink. Let's save that one. Start with b. Write a function h whose graph is a vertical stretch of the graph of f by a factor of 2. Now remember, that doesn't just mean place the 2 here, because we're taking the entire function and stretching it, which means we're even taking the -5 and doubling it, that kind of stuff. So what do? They take the entire function and they double it. So how do you double that? You double the entire quantity. You use parentheses. You distribute 2 the same way that we distributed, was it -1, into these right here. 2 times the absolute value function quantity. You technically could distribute 2 in here, but for reasons we're not going to talk about and for no productive reasons whatsoever, so leave it on the outside. Keep it in vertex form. We like to keep it like a vertical stretch, but 2 times -5 is -10 as well. So when compared to f, the one in black, the one in blue is twice as big. Now this one's a little different when it comes to transformations, because you don't just go twice as big from this vertex. You've now doubled the y value of the vertex. Notice how the x value stays the same. The x value stays the same. This is a vertical stretch, not a horizontal one. So it's twice as big everywhere. Every y got doubled. That includes the vertex. But every y got doubled and it's twice as tall. Let's go to the horizontal one now. Let's do a horizontal shrink of the graph by a factor of 1/3. Now, when you horizontally shrink it by a factor of 1/3, you do the opposite, the reciprocal, the multiplicative inverse, opposite of 1/3, and in the equation you actually place a 3. I know that's going to be confusing, but you actually place a 3 inside of there instead of a 1/3. Okay? Now go with me for a little bit as we talk about it. When they, and it kind of bothers me that they don't actually factor the 3 out, but I do want to talk about it here in just a second. A horizontal shrink by a factor of 1/3 multiplies each input value by 3. Keep in mind you would plug in x values that are 1/3 of what they normally would have been to maintain the same y values if the 3 wasn't there. 1/3 times 3 is 1. That's how it works. Anyway, so 3x goes in for your input right there. Boom. Instead of x minus 3, it says 3x minus 3, and that's their equation. Now, this isn't quite the vertex form that I would have preferred. Even if I wanted to keep the 3 inside there as a horizontal stretch compression factor, I still would have factored the 3 out of here. Not necessarily out of the absolute value function. I could, but I would have at least factored a 3 out of the quantity. Main reason, and I want to show you in the graph. Main reason is because this can still reveal some vertex form stuff for me. As far as translation goes, I don't go 3 to the right. I go 1 to the right. Look at the graph. Look how I don't know what the scale is. It looks like they go by 2s, 2, 4, 6, because this is a 3 right here. Look how this is not a 3. This is not 3 to the right of here. This is 1. This is 1 comma negative 5. That's what this point is right here. Why? It's horizontally compressed. It's 1/3 of what it was. This graph has now shrunk itself horizontally in this direction. That's what it is now doing. And in this case, it's horizontally compressing itself in that direction from the black. So it's getting itself 1/3 closer to, well, one third closer to the y-axis. Right? That's what all the points are doing. They're getting 1/3 closer to the y-axis than they ever were before. They're not shrinking into here, keep in mind. They're not shrinking into the vertex of this guy. They're shrinking into this line right there. That being said, factor this one out from here. I would and I will. If they ask me to graph these, that is absolutely what I'm going to do. They did it. That's why I'm surprised. I'm surprised they did it here. Notice they factored out the -1. I'm surprised they did it here, but they didn't do it in the other one. I think it was because it was a negative. But I would do it if it's any number in front of x when it comes to vertex form. I'll take it one step further. Remember that previous property I mentioned with absolute values? This is also the absolute value of 3 times the absolute value of x minus 1. And the absolute value of 3 is 3. So this equation can be rewritten as 3 times absolute value of x minus 1 minus 5. Why do I bring this up? Because this is conventional vertex form. This is the vertex form that you know very well, where your vertex is at 1, -5, just like we said. It's at 1, -5. And it's a vertical stretch factor of 3. But wait, Mr. Robinson, I thought you said it was a horizontal compression factor of 1/3. It's one or the other. It's exclusively one or the other. Now that we're calling this, now that the 3 does not exist inside the absolute value at all. We're not referring to horizontal stretches or compressions if you factor it out and get it on the outside like this. What was a horizontal compression of 1/3 has now been restated as a vertical stretch of 3. Are those the same thing? Yes. And that's the point I want to make. From here, you could say take a graph that was right here and stretch it 3 times more vertically. So now we're up 3 over 1, up 3 over 1, instead of taking what's there and squish it 1/3 of what it was. Squishing something 1/3 of what it was is the same as stretching something 3 times what it is. They're both the same. This is what I prefer to do. This is what I prefer to do in my equation. So we don't have to, if this part confused you, I don't blame you. Listen, we have to start there. But if this thing confused you as far as describing what you do, I don't blame you. If you can turn this into A as often as possible instead of B, and I say B because they use A right here, this is where I have to fight the book a little bit. I mentioned how I don't graph using tables, but the reason I'm spending a half hour talking about the lecture portion is because this is me fighting the book a little bit. I'm not blaming the book. There's nothing wrong with what the book's doing. Well, I feel like they contradicted themselves by not doing the factoring, but, and by the way, there are some functions that you can't really pull out a B into an A. When I think logarithms, you can't, but I don't know. I guess you wait for that when the time comes. But when you can turn something into something that's more commonplace and something that makes more sense to you, or at least that you can understand why the horizontal stretch compression works the way that it does, I want to talk about it, and I did here. Okay, I spent a lot of time on this problem. Let's go ahead and move forward and see what else they have to talk about. Combinations of transformations. So we're going to do multiple together. Stretches, shrinks, reflections, translations, whatever. You can write a function that represents a series of transformations on the graph of another function by applying the transformations one at a time in the stated order. Really, it's order of operations, but whatever they ask you to do. Let the graph of g be a vertical shrink by a factor of 0.25, followed by a translation 3 units up of the graph of f of x equals x. Write a rule for g. So the original equation is just this. Literally f of x equals x is basically as basic as you can get. So they first ask you to vertically shrink by a factor of 0.25. That means multiply 0.25 by your function. That's on the outside. That's like a. So it's going to affect your y values. So 0.25 times your function's just x, so it's 0.25 times x. Afterward, they add 3. It's a translation 3 units up. So it's a vertical translation. That means we add 3 to the new function. They're doing a combination of transformations. They're doing one at a time. They go from f of x to h of x. They go from f of x. H of x is kind of an intermediary step. They go from f of x to h of x for the vertical compression. Then they go from h of x to g of x for the vertical translation. The plus 3 happens after the 0.25 times. Will that always happen? No, it depends on the problem that they give you. But that's the only example they give you. So we'll see what else they give us in the actual problem set. Okay, modeling with mathematics. You design a computer game. My dear Aunt Sally. PEMDAS. Please excuse my dear Aunt Sally. Your revenue for X downloads is given by f of x equals 2x. So they give you a model there. That means for every X downloads, you make $2. You make $2 for every one download, I think. Your profit is $50 less than 90% of the revenue for X downloads. Ooh. Describe how to transform the graph of F to model the profit. What is your profit for 100 downloads? Those are two different parts, by the way. Okay, let's read what they say, and then we'll see if I should expand more. Understand the problem. You're given a function that represents your revenue, right there, and a verbal statement that represents your profit, right there. You're asked to find the profit for 100 downloads. That's an afterthought. Write a function P, okay, profit, that represents your profit, then use the function to find for 100 downloads. You take 90% of the revenue and minus 50. Notice how they said 50 less than 90% of the revenue. It's 50, you subtract 50 from whatever 90% of the revenue is. So first we take 90% of revenue, then take away $50. 90%, the decimal equivalent is 0.9 multiplied by your revenue stream. Your revenue is a function that's written as 2x, so we do 0.9 times 2x, which is 1.8x, and take 50 away from that, and then we get our function modeling how much profit we make as an overall. You see, this was revenue. Revenue is how much money you make. Profit is the net of revenue versus cost, right? How much you make as an overall when you talk about expenditures. 50 must be some sort of upfront cost, yada, yada. Okay, find the profit for 100 downloads. X is the number of downloads. You substitute 100 for X, so P of 100. This is that same thing as substituting for X. 1.8 times 100 is 180. 180 minus 50 is 130. You make $130 for 100 downloads. Okay, I'll move forward from that because that one seems a little more basic with regard to what we do, as long as you know how those things work. And that was one of the longer lectures I've ever had, especially when I speak philosophy. So I'm going to state this right now, and I'll probably state it in other times. If you want to hear more about what I'm argumentatively doing with respect to the horizontal compressions and stretches and stuff like that, you might want to look to the lecture portion and hear what I say. You might not get it, but that's where I speak on it most. All right, let's start with the vocabulary and core concept check. All right, number 1, complete the sentence. The function g of x equals absolute value of 5x minus 4 is a horizontal blank of the function f of x equals absolute value of x minus 4. This is one of the ones where we have to deal with this being inside. If I know they said a, I kind of have to use the letter b at times, I feel like. Your b value is 5. So therefore, you got to flip it and talk about this thing as a horizontal compression. I know their word is going to be shrink. Horizontal shrink or horizontal compression, where this is by a factor of 1/5. So if you saw the lecture portion, remember anything that is inside your function, literally this is inside the function, inside the absolute value. Anything that is inside your function, your x needs to counter it by doing the inverse of what's affecting it. If this thing's multiplying by 5, your x's need to be 1/5 of what they were. That's why this is a 1/5. Same with when something's inside, like, I'm just popping up a number right now, like this +1 right here. You have to counter it by making x 1 less than it is. That's why there's a -1. Whenever it's inside the function, you have to counter it by doing the inverse of what's in there. So it's a compression of that one. Okay, number 2. Which one doesn't belong? Which transformation does not belong with the other 3? Explain your reasoning. All right, translate the graph of f of x equals 2x plus 3 up 2 units. If we do that, that means we're going to make this thing 2 bigger than it is on y, so it'll be f of x equals 2x plus 5. Let's call this our A and compare it to the others. Next one down here. Stretch the graph of f of x equals x plus 3 vertically by a factor of 2. This one's a little tricky because here you are going to be doubling, well, not tricky, but here you're going to be doubling f of x, which means you're going to be doubling x plus 3, which is 2x plus 6. That's different from this one. Therefore, I'm going to call this b. Now, are the others a's or b's? I don't know. Shrink the graph of f of x equals x plus 5 horizontally by a factor of 1/2. Okay, this one's a little tricky because this one's a linear equation. Now, our function is literally just this guy right here. This is where it's tricky. It's just this right here. There's nothing else going on with it. There's no absolute value. There's no exponent. So it's just that x. So within that x there, or within the parentheses, I should say, horizontally shrinking by a factor of 1/2 means we have to write a 2 inside the function itself to counter that. So we're going to call it 2x plus 5. And now without parentheses again, it'll be 2x plus 5. These aren't easy. These aren't easy if you're brand new to this stuff. But guess what? That matches A. Same kind of thing. Last one, translate the graph of f of x equals 2x plus 3 left 1 unit. Same thing as before. Your function, now this can be argued one way or the other, whether you have the 2 here, inside, or outside. Literally, it can be argued either way, and either's fine. Actually, is either fine? Yes, either's still fine, I believe, when you do that. I'm going to do it like that. Okay. So inside your function, we're going to go left 1 unit. That means to make x's 1 unit left, we have to compensate by making everything 1 bigger. And there's the plus 3. So we turn 2x plus 3 into 2 times x plus 1 plus 3. Now if you distribute 2 into there, 2x plus 2 plus 3 becomes 2x plus 5. So it shows that all those are 2x plus 5. That's also an A. This B is different. Explain your reasoning. I did as much explanation as I could out of those. So this is the one that's different. That one does not belong. It's close, but not quite there. All right, guys, I'm going to go and jump into the official problem set. I'll see not only how long this goes with my argument of philosophy and stuff, but how much I do have to argue the philosophy of things. It goes up to 45 problems. I guess we have to go ahead and get started here. Let's begin with exercises 3 through 8, where you write a function g whose graph represents the indicated transformation of the graph of f. Use a graphing calculator to check your answer. I probably won't do that last part. That's for you guys to do. I can all but guarantee the answers that I give you should be spot on, I hope. All right, so f of x equals x minus 5. We are going to translate 4 units left. 4 to the left. Okay, to translate this thing 4 units to the left, what we're going to do is we're going to say g of x. Our g of x takes our f of x, and to go 4 units to the left, we have to add 4 to all of our x's, right? Our x's are going to be 4 more to the left, so we have to make them all 4 bigger to compensate. So what is f of x plus 4? X plus 4 has to substitute in for x, literally. Wherever x is, we're now going to have an x plus 4 there. And there's still the minus 5 because that's the whole function. So x plus 4 replaces x. The minus 5 is still there. And then this becomes 4 minus 5, which is negative 1. So g of x is x minus 1. Now, they say confirm using a graphing calculator. I do want to at least give you the idea of it if you didn't follow the lecture portion, which I really recommend for this section you do. If the f of x is this x minus 5 right there, and x being a slope of 1 like that, the x minus 1 is just right here where g is. Boom, boom. Now, you might say, hey, that's not 4 to the left, that's 4 up. Well, it is 4 up, but it is also 4 to the left that point is, and that's kind of the one that represents the corresponding part to the y-intercept. All right, let's go to number 4. On number 4, we have f of x equals x plus 2, and we're going to translate 2 units to the right. I like how shockingly cavalier they are about saying, oh, we're going to deal with horizontal ones first that are more difficult for people, and then we'll get to the vertical ones, which are much easier for people afterward. They even did that for the... They did it for all of them. They did it for the translations, the reflections, and the stretches and shrinks. They did horizontal first. I don't know why. So we are going to translate 2 units to the right. Okay, so our g of x will be taking our f of x, and 2 to the right means we got to make everything 2 smaller. Or, well, the x's are going to be 2 larger, so we counter by making everything 2 smaller like that. So we're going to take x minus 2 and substitute it in for x, where that becomes x minus 2. And there's a plus 2, and negative 2 plus 2 is 0, so you're just left with x. G of x equals x, which g looks like the parent function of a graph. Does that make sense to be 2 units to the right? I mean, if you know stuff about stuff, then sure. Because the x plus 2, I'm not going to do this much more, but the x plus 2 graph is right here. This is our f graph. I should probably put f. And g is at, boom, right there, like that. Is this 2 units to the right? Sure. Take a point and go 2 to the right like that. Seems to work out. Okay, number 5. I won't dare graph this one. I'm good. I'm good. All right, number 5. F of x equals absolute value of 4x plus 3, and then there's a plus 2. We shall translate. We shall translate 2 units down. This is where we now, our g of x is going to be taking whatever your f of x is and now affecting the outside, right? So this is going to be minus 2 for 2 units down. Whatever the y value is here, make it 2 less than it was before. So the f of x that was there is not going to change. It's still going to be absolute value of 4x plus 3. That's an absolute value symbol. Plus 2. And then we'll subtract 2 from it. Now, do I require using parentheses there? Absolutely not. Not for addition or subtraction of something outside of your quantity. But you will have to for multiplication. So I'm kind of giving you a good reminder that, yeah, you should probably look into it. So I'll rewrite the same thing without parentheses. Very redundant step to have happen. But 2 minus 2 is 0. So you're just left with absolute value of 4x plus 3. And I think most people would agree and understand that this is indeed 2 down from where this was. The plus 2 makes it 2 higher. This makes it 2 lower. Do you have to write all that work to make that happen? No. A lot of people are probably good with taking this one away. But it depends on the severity of the problem. So when we start doing the reflections and the stretches, it might be worth your time to actually put those in. And it's especially important probably when you're doing horizontal bits. Not that this one is. So let's see if we can do this one without use of, I don't know, showing the f of x thing. But translate 6 units up. Because this one's as basic as it gets, I believe. I'm serious. I think this is as basic as it gets with what you do. G of x takes your f of x, and we're going to make it 6 units up by adding 6 to it. Adding 6 to the f of x. And negative 9 plus 6 is negative 3. So that's as easy as it can get. 2x minus 3 instead of 2x minus 9. Yeah, that seems 6 higher. And remember, that's affecting y. So hopefully you kind of understand the gist of how that can be simple. But it's not always. All right, let's go to number 7 and 8. I think it's the same instruction. Oh, so on these ones, I mean, it's part of the same, this is part of 3 through 8. So it's part of that same instruction above. So let me copy that over because it's a graph. So this is f of x equals 4 minus the absolute value of x plus 1. I'm a little more keen on seeing this in that proper vertex form. I'm going to rewrite it with the x plus 1, the absolute value is still negative, and the 4 is still positive, but I'd rather kind of see it like that. Hope that's okay. Anyway, so there's the original f graph. Now what happened, sorry, it's right here. Here's the original f graph. Now what happened to g? It looks like it's translated 1, 2, 3 to the right, and it's much more easily recognizable. I should probably say translate 3 to the right. It's much more recognizable in an absolute value function which way you translate because there's a vertex there, whereas a linear function doesn't change its behavior ever. So if I'm translating 3 to the right, g of x will be taking your f of x equation, and 3 to the right means 3, the minus 3. Opposite inside there. So how does that work in your, let me keep it black. How does that work inside your substitution of this thing? Here's f of x, negative, and replacing x will be x minus 3. X minus 3 will be replacing x. There's still a plus 1 inside the absolute value function, and the plus 4. So your absolute value function is now 3 less than it was before, and we'll show that through simplification. What is negative 3 plus 1, or 1 minus 3? Negative 2. So all that changes is that inside, like that. There's a new graph. Now, if you know anything about vertex form, your vertex is at 2, 4, and that seems to agree. I guess that's another way you can do it, right? You just know the vertex form and say, hey, let me write it. And that would be it. All right, let's do number 8. Number 8's kind of small on the graphing front, but we're going to still discover what it is they're doing. They're all translation based, so at least there's ease on that. We know it's not a reflection or a stretch or anything like that. And we'll get to those. Let's put it here. All right, number 8. Now this, I just want to speak on this part really quickly. This is, again, where this could be rewritten as 4 times absolute value of x plus 5, because absolute value of 4 is 4, and it's a product and all that stuff. So you can either treat this like a vertical stretch of 4, up 4 over 1, or a horizontal compression of 4, over 1/4, up 1. I'm not really big on horizontals. Anyway, either or, it still works out, but the question is, how is G affecting this thing? Or what's G in comparison? Looks like we're translating 1 up. Translate 1 unit up. So to translate 1 unit up, G of x takes your f of x equation and adds 1 to it, literally. So you take the f of x equation, whether it's this or that, I'll just take the original, whatever, for x plus 5, and then, a good old plus 1, right, to that whole thing. To that whole thing is the 5 plus 1, and 5 plus 1 is 6. So G of x equals absolute value of 4x plus 6. Or 4 on the outside, as I so prefer. Now, I'll definitely have to stick the landing on more of those just so you can comfortably do it and recognize what it is that I'm saying when I do it. Either or is fine. And if you know anything about the vertex form of a graph, I think you'd agree that that's correct. Okay, let's keep moving down to number 9 on writing. Describe 2 different translations of the graph of f that result in the graph of G. It's one of those things, again, where I can either copy and paste the graph over or just leave it as it is. I think I'll copy and paste it over so my markings are a little more pronounced. I can make the graph a little bigger. So G is the one in blue, F is the original, and this is where your translations can either be vertical or horizontal. I guess you could do both, but I think as far as an answer that they're expecting, they'd probably just want one or the other. Let's talk about a vertical translation first, especially when you see it on the y-axis, right? The y-intercept, rather. I'm trying to make an orange arrow. So there's an orange arrow right there. What can you tell? This translated up 1, 2, 3 units. I mean, that's true anywhere from here. 1, 2, 3 units. So when they say describe 2 different translations, we can say translate 3 units up. Or we could have translated, it looks like 3 units to the right. 1, 2, 3, like that. We can translate 3 units to the right. Either or will apply the same answer. Or the equivalent equation. I want to keep getting into it. So if we did translate 3 units up, like literally, if we took this equation and did what we were doing from previous questions, we would be saying that g of x equals, you take your f of x and you add 3 to it. So you'd be taking negative x minus 5 and adding 3 to it. Negative 5 plus 3 is negative 2. That's negative x minus 2, and that matches that answer. Now, if we do 3 units right, your g of x equation, you take f of, and then inside the equation, you do x minus 3. This is where it gets a little trickier, right? The x minus 3 happens. So 3 is to the right is there. So inside here, x minus 3 substitutes for x, but you got to use parentheses. There's a negative on the outside. Oh, where is it? Where's our equation? Right here. There's a negative on the outside, and in for x goes x minus 3 in parentheses. When you distribute the negative, you get negative x plus 3, and 3 minus 5 is negative 2 again. So you get the same thing as you got up there. It gets tricky, but that's why I want to keep bringing this up as often as possible when we do it, why this works both ways, but why you got to use parentheses, why the substitution is important, why we flip the sign. All that stuff applies. That's number 9. Okay, these are the 2 answers, though, by the way. Okay, let's see what number 10 is all about, because I have no idea. It's problem solving. Hey, number 10. And this is still translation-based, I'm sure. You open a cafe. The function f of x equals 4,000x represents your expected net income in dollars after being open x weeks. So 1 week, net income of $4,000. Before you open, you incur an extra expense of $12,000. What transformation of f is necessary to model the situation? How many weeks will it take to pay off the extra expense? So there's that one. Let me make a g of x equation here. The g of x equation, the expense, the upfront expense of $12,000, it says before you open, which means it doesn't change as time goes on. It was an upfront one before we started. And an expense is opposite of income, results you'd subtract. So subtract $12,000. You take, let me write it this way. You take your f of x and subtract 12,000, and that'll turn it into that. So g of x equals 4,000x minus 12,000. So that's the equation. They asked what's the transformation. If that minus 12,000 is on the outside of it, it's a translation down. I mean, imagine the graph represents up is positive income, down is negative income, things like that. You translate 12,000 units down. Now this is $12,000 down. $12,000 down. Yeah, from your original, right? That was the incurred expense. How many weeks will it take to pay off the extra expense? They're asking, when will your when will you break even? When will 4,000x minus 12,000 equal 0? Or better yet, when will 4,000x equal 12,000? When you add 12,000 to both sides, divide both sides by 4,000, you get x equals 3. That means it'll take 3 weeks to pay off the extra expense. You're going to make $4,000 a week. For 3 weeks, you'll get up to $12,000. You'll pay off the expense. You'll have broken even. It will take 3 weeks. I lost my mouse cursor. It will take to pay off the extra expense. Okay. All right. Water hit, then 11 to 16. Okay. Numbers 11 to 16. Write a function g whose graph represents the indicated transformation of the graph of f. Use a graphing calculator. So it's the same stuff as the original problems, but now it's not on translations anymore. Now it looks like reflections. So I think it's going to go kind of fast here. So f of x equals negative 5x plus 2. Let's reflect in the x-axis. That's the one that we've done more often. Reflect x-axis. Okay, so g of x takes your f of x and changes its sign. It makes it opposite. It's the entire function, though. This is where those parentheses will be of utmost importance. We're not just turning the negative 5 positive. We're taking every term in the quantity, and when we simplify it, might change all the signs. Distribute a negative 1, we get a positive 5x indeed, but the 2 turns negative. Everything flips over. There's our new g of x equation. The graph is a confirmation. Negative 5x plus 2 would have a y-intercept up there as it goes down, and positive 5x minus 2 would go this way. Negative 2 y-intercept and goes that way. Here's the reflection across the x-axis like that. Okay, let's look at number 12. Another linear equation. I will probably not bother graphing it, but, well, it depends. Well, it's a reflection in the x-axis. No, I'll keep it. F of x equals 1/2 x minus 3. Let's reflect across the x-axis. You know, when handwritten typos, when I do the same thing over and over. Same thing as before. G of x, we're going to make the f of x negative. That means change all the signs, distribute that negative, and we are going to get negative 1/2 x plus 3. I'll just be done with the problem then and there. I hope that satisfies our needs for it. Number 13, we are going to reflect in the y-axis. Now, this is where I get to be a little creative, or the book also got a little creative, but I'll take it even one step further. F of x equals absolute value of 6x, then minus 2. Reflect in y, the harder of them. So reflecting y-axis, keep in mind, that means take your f of x equation, but make every x a negative x. That's what's going to be substituting into there. So g of x equals, this will be absolute value of 6 times negative x minus 2. X got replaced by negative x. Should have made it blue, my bad. Not that you can really tell. And that would make, I'm skipping every other line here. That makes that a negative 6x, minus 2. This could be an answer. It's just not the simplified forms that they look at. Last time they factored a negative 1 out of here, but I'll go one step further. I'll factor the negative 6 out. Keep in mind, this is negative 6 times x. An absolute value of a product can equal the product of two absolute values, like this and like that. I don't know if, like, the back of the book, because it's an odd number problem, I don't know if the back, I assume the back's just going to have the negative factored out. I'm going to factor the negative 6 out. Absolute value of negative 6 is 6. And here's our other equation that looks like that. So it's this one. And hey, guess what? The original equation, remember this one right here? You could factor out the absolute value of 6 in the same way. So absolute value of 6 times absolute value of x minus 2. And that becomes 6 times absolute value of x minus 2. Now here's the interesting part. That's not the answer, by the way. But here's the interesting part about both of these. Take a look at them. Take a look at them. Take a look at them. What do you see? They're the same. Why are they the same? Let's graph this one. Remember, you might know how to do this one a little bit more. Vertical stretch of 6, the slope is 6, things like that. This is a horizontal compression of 1/6. That's kind of weird. But what do these ones look like? This one's got a vertex of negative 2, down 2 like that, and then we go up 6 over 1 like that, and all that. Besides looking at this equation, because it's literally the exact same thing, what is this graph? What was our instruction for this? Oh, reflected over the y-axis? You mean this one? What happens when I take this V-shaped graph, which already has symmetry at its vertex, and reflect it over the y-axis, flipping it over? You get the same thing. You get the same graph. It's literally, how does it change? This is that reflection piece. So that's why I kind of like seeing it in this form, and what you do when you simplify it. They're the same thing. They're the same thing. Is that always the case? Well, obviously not. But yeah, that's why these are equivalent there. All right, let's go to number 14. Good deep exploration, right? F of x equals, and I'm not going to graph this one, but f of x equals absolute value of 2x minus 1, then plus 3. F of x equals absolute value of 2x minus 1 plus 3. Reflection in y-axis. Once again, the question is, how much am I going to conflict with how the book would instruct something here? I'm going to be doing f of negative x like the previous one. I'm not going to change colors anymore here. So that's absolute value of 2 times negative x minus 1 plus 3. 2 times negative x is negative 2x. So absolute value of negative 2x minus 1 plus 3. My guess is the book would just factor the negative out. So if I'm going to follow a book strategy, it would be this. I'm going to say book. So what the book would do in this case is they would purely factor the negative 1 out, and you'd be left with 2x plus 1 inside here. And then, as you've seen probably a couple times now, remember it's a negative 1 multiplying by that. That means the negative 1 can be factored out, or it is factored out. It can be written in its own absolute value, while the 2x plus 1 is written in its own, and absolute value of negative 1 is positive 1. So they'd have their answer written like this. It's not terrible, but if you were to graph it, see, they insist on graphing using a table. I use vertex form, different story. But here's an answer. It's a fine answer. It works. And when you compare it to the original, slightly different. This has a negative 1, that is a plus 1, but don't make the mistake in thinking that means translate 1 to the right and translate 1 to the left, because that would be wrong, and that's why I wouldn't agree with the book there. So what would I do? Mr. Robinson, same-ish with one bigger exception. I won't factor out negative 1. I'm going to factor out negative 2. At every expense of this 1 turning into a fraction. You might say, oh, I don't like that. Negative 2 times what is negative 1? Positive 1/2. So that's how I'm going to write it. And the same thing happens here where, the negative 2 gets its own absolute value bit. And then absolute value of negative 2 is positive 2. So I'm going to rewrite it like this. Positive 2 times absolute value of x plus 1/2 plus 3. So that's my version of the answer. Either or should be fine. They should be simplified versions of what you have. Why do I prefer this one? Despite the fact I prefer talking about vertical stretches more than horizontal compressions, the true translation of this graph is 1/2 to the left. It's 1/2 to the left. Now, that also means the original graph could have been rewritten as f of x equals 2 times absolute value of x minus 1/2 plus 3. So what's this true's graph translation? 1/2 to the right. That's the part that there's going to be a little bit of hiccup with me in the book. And that's where I'm going to be talking about both as often as I can, especially when they start making us graph them. Even if, listen, are you listening? Even if I kept the 2 inside, even if I kept the 2 inside and made it a horizontal compression by a factor of 1/2, I still would want to factor it because I still want to represent my vertex, my horizontal translation here, even if I kept it inside. Now, I absolutely want to factor that negative out. It has no weight in this problem whatsoever. I have no need to reflect a absolute value graph. I still get the same thing out. So there's no reason to be doing that. But I want to see my true h value, and my h is negative 1/2. So whether I keep it inside or outside is up to you, or up to whatever we do, but I am going to factor that out. I graph out a vertex form. That's what I'm going to do. Okay, a lot of me talking. Number 16. Probably not one of the videos that you're like, come on, move forward. F of x equals negative x plus 1. Kind of seems like a basic problem in comparison. Reflect across the y-axis. Okay, so this one, your g of x, you got to flip the inside right there. So we're going to be taking the opposite of negative x and plus 1. Opposite of negative x is x, and you get x plus 1 is that linear equation equivalent. Instead of a slope of negative 1 like that, it's a slope of positive 1. Whoops. Slope of positive 1 like that. So that's the difference in the graph. It's a reflection across the y-axis, not the x-axis. And you're good. Okay, that is 11 through 16. Let's move forward. Exercises 17 to 22, we're going to start doing vertical stretches and shrinks, horizontal stretches and shrinks. Write a function g, use a graphing calculator. No. Let's do one of each, it looks like. Number 17, we have f of x equals x plus 2. We are going to vertically stretch by a factor of 5. So g of x takes the f of x graph and makes everything 5 times bigger. That includes the 2. Every y value becomes 5 times the size of what it was before. That means we're doing 5 times the function, not just x, but x plus 2. If I distribute and make it slope-intercept form, it'll say 5x plus 10. So 5 times bigger. 5 times bigger. 5 times the slope, 5 times the y-intercept, 5 times the fun. Number 18. F of x equals 2x plus 6. Vertical shrink. I'll put compression factor. Vertical compression by a factor of 1/2. The 1/2 gives it away. That's what I'm doing anyway, but it's vertical, and vertical is different from horizontal, right? It matters in how you do that. So we're going to 1/2 that f of x that we have, which means we're going to take half of 2x and half of 6, which means divide them by 2. So distribute the 1/2. Half of 2x is 1x. Half of 6 is 3. G of x equals x plus 3. Okay, numbers 19 and 20 are absolute value functions, and they seem to want to go straight into the horizontals with the absolute values. I guess not the vertical. Oh well. Number 19, we have f of x equals absolute value of 2x plus 4. The 2 in here already means it's horizontally compressing it by a factor of 2. Now they want to do it, or of 1/2. Now they want to do it even more so. So they have a horizontal compression by a factor of 1/2. Now, as far as what you want to do in here, this means this. Whoops. This means for g of x, you take your f of x function, and you are going to, remember, a horizontal compression, take the reciprocal, take its inverse, that becomes 2 inside here. You double whatever's inside because x needs to counter and be half of it. Now, this can look a little confusing because you already have a 2x inside there. You're like, what do I do? Well, 2x is going to replace x. Don't worry about the other 2. Worry about it. It's going to be there. But don't just say, oh, there's already a 2 there. I'm just going to ignore the 2 that I put. No. That's like saying take the negative that was right here, and ignore that negative. No, it's still there. It's still a part of it, right? This this negative x is right there, but there's still a negative on the outside, just like right here. There's still a 2 right there. So what are we going to do? Our equation will now look like absolute value of 2 times, and for x is 2x, plus 4, which will look like 4, absolute value of 4x plus 4. Now, I'm not doing a lot in the form of graphing it or describing the transformations or factoring the thing out right there, but before, what was a horizontal shrink by a factor of 1/2 is now a horizontal shrink by a factor of 1/4, because you just took half of a half. So that's the effect of it, at least, and that's what we're seeing. Number 20, and like I said, the book's really going to stress the horizontal stretches and compressions, because I guess they just gotta, but they're really, really giving it its light. And I'll be honest, I believe this was when I was first doing my textbook solution guides, when I did it for IM2, and it was the very first section that I did. I believe those ones did horizontal stretches and compressions, and I kind of ignored them outright. I said, look guys, I'm going to factor them out. Go to my 1.1 video at IM2. You're going to see I factor them out right. I just do it. So I'm not big on them. I'm not big on them. All right, anyway, horizontal stretch by a factor of 4 means everything's going to be 4 times as big. So g of x, we got to, if everything's going to be 4 times as big, we got to counter that with that having everything 1/4 the size. That's what makes x's 4 times as big as they were. Those should totally be parentheses, my bad. So that goes inside of there because it's horizontal. And let's take a look at what happens here. So g of x equals, remember, it's going to be replacing x. So absolute value of 1/4 x and plus 3. In some cases, that's it, right? That's all you'd put. Now, if it were up to me, I would be doing this, because guess what? 3 is, we don't translate 3 to the left, but I would be writing it like this. At the very least, I'd be factoring the 1/4 out of the quantity and turn it into x plus 12, right? 1/4 of 12 is 3. I'd be writing it at least like that, because now I know that you translated 12 to the left, not 3 to the left. But one or the other, all good. Okay, oh, look, there's some more. So 21 and 22 are a part of these. Oh, good, we get an absolute value function with a vertical stretch conversation. So number 21, let's go ahead and copy and paste that one and see what's going on with it. This is where you have to start observing. Take a point and its corresponding point and ask yourself how the y's compare to each other. That's really your best bet, unless you start plotting every point in a table. So with this one here, here's the original function f that's in black, and in blue is the new g, which we're making. And what's happening here? Take the vertex as your best example of it. They're showing you right here. The 4 stays the same on x, so it's no horizontal change, but there's a vertical change from 2 to 1. It became half of what it was. Don't call it a translation, because not everything else translated right here. The zeros stay as 0, and then everything else kind of changes with it. So it's a vertical compression. There's a vertical compression factor of 1/2. That means g of x is half of f of x. So we're going to write its equation by taking half of, I'm not probably going to be able to fit this, by taking half of the whole thing. -2 times absolute value of x minus 4 plus 2. Now we got to distribute the 1/2 into there. 1/2 times -2 is -1. That's on the outside. I'm just going to write a negative. The x minus 4 still remains as it is. It's part of the same quantity as that. And then 1/2 of 2 is 1. And this is your resulting equation. Does this match up? Do you know how vertex form works here? The vertex is at 4, 1, 4, 1, yes. The stretch factor is negative, it's flipped over, but -1, down 1, right 1, yes. Yes, it works. Okay. Well, there's number 21. Let me start copying number 22 as you absorb that, or pause the video. Okay, let's go to number 22. Copied and pasted. Not even halfway done here. How far have I got? An hour 9. All right, f of x equals 6 minus x. Well, you know me, slope-intercept form, I'd rather write it as -x plus 6. That's how we see it, right? Slope of -1. Really? Oh, these scale these scale by 2s. That's just mean. These scale by 2s and these scale by 1s here, but I guess that's down 1 over 1, down 1 over 1 like that. So do what you got to do. Anyway, what are we doing here? G. How does G compare? Well, it's a little tricky because I guess here's where they're getting you. It's not a vertical stretch or compression technically, because notice how at some x value, the y value stays the same. That's not the origin. So you can't say something like, oh, you double it or something like that, right? Because otherwise the y value would be doubled. No, this is about horizontal compression. So they're forcing it on us. I could have different ways to write this, meaning if I know my slope intercept form, this is down 6. Here's one answer I could write, right? G of x equals negative 6x plus 6, and like, boom, there's my answer. But that doesn't really explain what I really want to say about it, right? So what do I really want to say about it? Let's pick a point and something that, a reference point, something where it moves from here to there. That's quite obvious. This was 3 away from the y-axis. Now it's 1 away from the y-axis. What's the change? Horizontal compression by a factor of 1/3. For us, no, I'm sorry. This was 6 away, right? Look at the scale. That's mean. This was 6 away. Now it's 2 away. I guess that's still horizontal compression by a factor of 1/3. So horizontal compression by a factor of 1/3. Oh, then that's not a negative 6, actually. What is that? That's down 6 over 2. So that's negative 3. That's right. Anywho, what were we talking about? Horizontal compression by a factor of 1/3. So g of x, you take your f of x equation, but for your inputs, you got to remember triple it. So 3x, like that. So anytime you see x, replace it with a 3x. So negative, and in parentheses, 3x and plus 6. Multiply the negative by 3x, you get negative 3x. So negative 3x plus 6. And hey, you get the same answer as what you saw above. They were kind of mean on the scale, but they're testing me as well as they're testing you, I guess. Okay, let's do numbers, 23 to 26. And in these exercises, it's a multiple choice thing. In exercises 23 to 26, match the graph of the transformation of f with the correct equation shown. Explain your reasoning. These are all about translations versus stretches and compressions. Okay, so number 23. Listen, I don't know if I have much to, I don't know if I really want to copy paste the graphs, but I can do overlay. Well, yeah, let's do this. Let's kind of do overlays. If this works out, fine. Sorry if it's going to get a little big, but I'm going to try this and see if it works okay. If it doesn't, then oopsie. So here's the original graph, and let's see if this thing can overlay pretty well. See that? All right. So check that out. So the original f was, I'll mark the other one G. So this guy, I'm going to mark G. So what's the difference between this guy and that guy? Looks like it's just a translation. We take this, pick it up, and move it over. We translated some amount of units to the left, but we translate left, which means we have to affect the inside of your function with a plus of some sort. So we're looking at option C. Now option C would be it because it's the only one that has an inside translation. So that's option C, y equals f of x plus 2. Translate left is my explanation, by the way. All right, that's number 23. Let's go to number 24. I'm trying to do the same thing. I think that kind of worked out. So on number 24, let's take the original, again, parent function. Let's see if I can just keep this on the side here. Whoops. Keep this on the side like that. Okay. So I have that guy. Not parent function, but the original function. Excuse me. And now we have this guy here, and that's kind of cool. There's our f, this is our g. Okay, what changes? Horizontally, nothing's changing, neither by translation nor stretching, because the vertex is still in the same spot. It's not like it went twice as far away. Vertically, no translation, but it did stretch, right? So even at 0, it's still 0, but now it stretches upward. So we're looking at something that affects your f function by multiplying on the outside of the function. So that'll be option A. I really shouldn't keep this thing circled, but that'll be option A. So this is a vertical stretch. That's the reasoning. So the answer here, option A, is y equals 2 times f of x. Apparently everything's doubled. Whether or not I understood that is, I didn't know everything was doubled, but that's the only option that's possible. All right, let's go to number 25. By the way, we can now take out A and C. Either B or D is left. So on number 25, Let's go to the next side here. $25. We got this new guy here. Okay, what does it look like to you guys? To me, it looks like a vertical translation. Vertical translation, and it's going up. So we're gonna add probably +2 again. So D would be this answer on this one. Y equals f of x plus 2 takes your f of x equation 1 up, 2 up, red up, blue up. You already know. And then number 26, by process of elimination, it must be B, but let's see why. It must be, now remember, it should be a horizontal compression on this one, by the way. Oops. Sorry that I'm making them so big. It's just that I don't want to have to resize them after and resize them by the same amount. So hopefully it just fits on the page and you're all good from that. All right, so number 26, is this a horizontal compression? Does it make sense that it is? Well, let's talk about why it's a compression and not a translation. You might say, oh, look, it moved over. Yeah, but not everything moved over by the same amount compared to the first one that we talked about. That was literally just to take it and slide. This thing is shrinking it closer to the y-axis, literally. It's taking everything and making it twice as close as it was before. This is twice as close as it was before. This is twice as close as it was before. This, I'm pointing at the wrong thing. This is twice as close as it was before, things like that. This is twice as close as it was before. So this is a horizontal compression. Now, what you have to keep in mind by horizontal compressions, or horizontal shrink, is that inside the function, it's going to look like it got bigger, like 2 times x. So that'll be option B, which, yeah, says f of 2x. So option B, f of x equals 2x. In the same way, right, that'll look up. Whoops. What did I just write? Y equals, what did I just do? Y equals f of 2x. Remember, in the same way that the horizontal translations are opposite, you see that plus on the inside, you go 2 to the left. You see the 2 times on the thing, it means you go twice as small, horizontally. Okay. Numbers 27 to 32. Write a function g whose graph represents the indicated transformations of the graph of f. So this is where you have the combinations of them. So we have original f of x equals x, and we're going to do the following. Vertically stretch by a factor of 2, and then translate 1 up. It's one and then the other, right? So what they kind of did before, you know, you can write this in 2 steps or in 1, but or 2 different steps or 2 things in 1. But what's important is that you know your order of operations here. You got to do the times 2 to this thing first, and then you do 1 up after. So I'll do it one at a time here to begin with, and then we'll see if you want to change something after. I'm going to have an intermediary h of x, which is just going to be doubling the f of x. I'm going to do kind of all the steps that the book would have done, which is 2x like that. Now your g of x equation after that is the one that takes the h of x, and then it translates 1 up, right? That's what comes afterwards. So they're both affecting your y values, a vertical stretch and a vertical translation. So 2 times on the outside plus 1 on the outside. So this is 2x plus 1. Could have you done that in one fell swoop and just gone straight from here to there? Yeah, it's possible. Absolutely. I'm sure by number 30, I want to do exactly that. That's number 27 to begin with. Number 28, f of x equals x. We're going to translate 3 units down, followed by a vertical shrink by a factor of 1/3. This is where you got to be careful, because notice they mentioned translation first. That does matter. It is important. Translate 3 down, and then vertical compression by a factor of 1/3. So with this one, notice this answer will not be 1/3 x minus 3, because the translation has to happen first. So it's not that. Okay? Now, if I do the whole in order thing, you'll notice that h of x takes your f of x and subtracts 3 first. That's the translation 3 down. So that's x minus 3. But now your g of x afterward takes your h of x and makes it 1/3 of what it was before, that means you have to do, and here's the important part, and I'll try and jump into these on the next set of problems. You're going to take 1/3 of x minus 3. There's a difference between 1/3 x minus 3 and 1/3 of x minus 3. When you distribute the 1/3 into here, you get 1/3 x minus 1. That's the difference there if the translation happens first. So if an addition or subtraction occurs first, guys, use parentheses around your item. And that's what I'll do in the future ones to kind of just, ease it up so I don't have to do all those extra steps if it doesn't feel like it's needed. If you're learning off it, really. Number 29, absolute value of x is your parent function. So f of x equals absolute value of x, translation 2 units to the right, followed by a horizontal stretch by a factor of 2. Now I almost feel like I need to go back to the other steps because they're things that go inside the function. So it's probably best that I just do it like I have been doing. So translate 2 to the right. Maybe on number 30 we can make sure that our order is fine. Followed by a horizontal stretch factor of 2. So notice how translate to the right. This is going to be the same kind of thing as you just saw. The 2 to the right needs to kind of be in parentheses here. And I think that goes to speak about what I've been talking about with respect to the thing. Factoring out that number inside of your function so you can reveal the true h. Anyway, 2 to the right will be an x minus 2. So this is going to be looking like absolute value of x minus 2. But your g of x means we still have to do the horizontal stretch factor of 2. Now, two things have to be in mind. First of all, it's going to be inside of your function. Second of all, stretch factor 2 means this needs to be a 1/2. Okay? So 1/2 of I wrote something wrong. I don't know what it is. I want to think about that. This isn't what I... Oh, never mind. You know what? This is right. It said followed by a horizontal stretch factor 2. Okay, we're good. This is fine. This is fine. I was thinking this needs to be in parentheses. No, it doesn't. It's only if it's the other way around. Because when we do our translations on our graphs, we're makeshifting the translation first when it shouldn't be. Okay, we're good. So this would be the answer. A better answer to me is g of x equals, at least, even if it's still inside there, factor that out, and this becomes x minus 4. Okay, we're good. This or that. Honestly, that was the one you're going to see in like an answer book. Number 30, f of x equals absolute value of x, reflection in the y-axis followed by a translation 3 units to the right. Yet they really like to do the horizontals on the absolute value ones and leave the vertical ones for the linear. So, reflection across the y-axis, followed by a translation 3 units to the right. Okay, let's see it. Let's stick to kind of book order. There's nothing, what the book's doing is fine. Reflection in the y-axis means change your input, change that sign. So it'll be absolute value of negative x, which, as we've seen, when you factor that negative 1 out, actually just becomes absolute value of x. So no change, right? If I take absolute value of x and flip it over, still the same graph. So nice. No change there. G of x now takes h of x or f of x, whatever, and goes 3 units to the right. So that's f of x minus 3. 3 to the right like that is going to look like absolute value of x minus 3, like that. X minus 3 is replacing x in that function. Oh, I wrote f. I technically should have written h, even though it's going to be no change in my answer, but that should be an h. And there we have it. That's it. All right, let's see if I can do something on numbers 31 and 32 and just go straight into... I got to be careful to not just say, here's the vertex form answer, and actually say what's happening from one thing to another. And it's like I can choose my order, right? All right, so number 31, we have an original. Oh, let me copy and paste this. Hold on. We have original absolute value of x parent function there, and then it turns into some g. But there's an intermediary step in between. Now, the first thing that I like to just kind of call witness to is the reflection. This thing's flipping over first. And I want to say the flip over first so the translation's significantly more manageable. Now the slope seems to stay as that, or stretch factor seems to stay as that -1. There's no real change in that. So this thing seems to just reflect over this way, like that, and then it translates downward, right? We flip it over, and then we go down this amount. Now it looks to also be scaling by 2s. That's not going to matter for our reflection. But first thing is reflect across x-axis. And then we translate from 0 to looks like -8. So 8 units down. So can we now take this? Are we good enough that we can maybe take this equation and go straight to g? G of x, here's the h of x, negative absolute value of x, right? H of x is negative absolute value of x. That's the reflection. But then we take that thing, right? There's the flip over. And 8 units down is subtracting 8 outside of that function there. Remember, reflection happened first, so if there were any parentheses, it would start here. You wouldn't translate 8 and then reflect. That's where there's a difference in what you do. So that would be the final result of what's there. Number 32, again, absolute value of x function. Looks like it's just a translation, series of two translations. And the scale also looks to be normal, and that looks to be big. So let's look at number 32. Bing. Yeah, guys, what are we doing? We're just doing 2 translations. We're going to translate right then down or down then right. Doesn't really matter which way. But 1 unit right and 1, 2, 3 units down. You know, I kind of just want to write the vertex form equation. I think it's worth us knowing what that is. X minus 1, not quantity squared, absolute value of x minus 1, and then minus 3. That's translate 1 right. Right, that's the whole x minus 1 portion. And then translate 3 down. Okay. Okay. Moving on up. Let's go. Numbers 33 and 34 are error analysis. Oh, I expect a horizontal stretch to show 2. Or, you know, to show a number more than 1. I fully expect that. All right, number 33. F of x equals absolute value of x, translate 3 units to the right, followed by a translation 2 units up. Oh, or this backwards part, right? Instead, 3 units to the right should say absolute value of x minus 3, and it says absolute value of x plus 3. So that's the mistake. So, their mistake, they have absolute value of x plus 3 in equation when it should say absolute value of x minus 3. I mean, we can dig deeper into the y of the matter, but the whole formula aspect, right? You do the opposite of what's inside there. So really that's it. I mean, we've said it enough, so I'm going to do that. G of x equals absolute value of x minus 3. The plus 2 is correct. 2 units up is going to look like that. So again, this is one of those things where more of, I'm sure most people don't really still understand why you do opposites. Even though I've said it a bunch of times here, but people still don't understand why. As long as you know to do it, that's good. I would definitely love to know the why for sure, but keep probing me on that if you want to hear about it, prodding me about it if you want to hear about it more. Number 4, we're going to translate this linear function 6 units down, followed by a vertical stretch by a factor of 5. Okay, so the interesting one about this is if you go 6 units down first, then that has to happen first. The stretch factor of 5 happens afterward, and it affects the 6 units down. You're no longer going to be six units down. You're going to be 5 times that amount. So you really need parentheses around that. If subtracting 6 occurs before, I should say translating. If translating occurs before a vertical stretch is applied, the subtraction should be quantified in parentheses for order of operations, for proper order of operations to take effect. Right? You want to do the subtraction first, and then the multiplication, which affects the subtraction. So the way we've been seeing that before is like doing this h of x in between and stuff like that. But no, if we're going to do, because they have the numbers right, the idea, but this x minus 6 should be in parentheses. This isn't saying translating 6 units to the right, so to speak. This is just saying do the, actually, let me do it like this. They're saying it more like translate 6 units down, okay? Translate 6 units down, and then make it 5 times bigger. Everything 5 times bigger. So now we go ahead and distribute and get 5x minus 30. Yes, yes, yes. It's a big low y-intercept. Okay. Number 35, making an argument. You know, for all told, I guess because we're not doing very many graphs, we've only been doing the problem set for an hour, and we only have like 11 problems left. I was going like, this is going to be a 3-hour video. I don't know. Maybe it still will. I don't know. Your friend claims that when writing a function whose graph represents a combination of transformations, the order is not important. Is your friend correct? Justify your answer. Your friend's not correct. Dude, we just did problem number 34. Of course it matters. Of course it matters. So, yes. Well, my friend is incorrect. Order absolutely matters, especially when translation is involved. Against reflections / stretches and shrinks. All of them. Because that's an order of operations thing, right? Reflections, stretches, and shrinks either means making something negative or multiplying by something or dividing by something, which is really a way of saying multiplying by something, right? Division is multiplying by something. Making something negative is multiplying by a negative. Translations are all addition and subtraction. This is a PEMDAS thing, right? In the world of PEMDAS, multiplication occurs before addition. And remember, addition also means subtraction because it means addition of a negative. Unless prioritized by parentheses. If you translate first, have your addition or subtraction in parentheses. Right? That changes the order. Yes, the order is important. It turns your 5x minus 6 into 5x minus 30. Right? If I translate and then reflect over an axis versus reflect over an axis and then translate, I'm in 2 different spots. Okay. Number 36. A lot of words. During a recent period of time, bookstore sales have been declining. Yeah. The sales in billions of dollars can be modeled by the function f of t equals negative 7/5 t plus 17.2, where t is the number of years since 2006. All right, for me to interpret this right now for you, it's this. There are 17.2 billions of dollars of book sales. Every year, you're losing about $1.4 billion in overall book sales. It's not that they're losing money. They're just making less money than the years previous. So in the year 2006, they probably made 17.2 bill. All right, suppose sales decrease at twice the rate. How can you transform the graph of F to model the sales? Explain how the sales in 2010 are affected by this change. Yeah, so you initially have some, twice the rate. You initially have some F of t here. Now, the important thing about the twice the rate, they say twice the rate, but that constant still needs to be what it is, right? The only thing that you're doubling, I'm going to have to call this a g of t or something like that. The only thing you're doubling in my assessment of this problem is just the negative 7/5 t. I feel like we're not doing anything to the 17.2. You know, this can speak, okay, here's what they probably want. This can speak more to reason why horizontal compressions might matter. Because if you're thinking about vertical stretch, I get, sales decrease at twice the rate, so they're decreasing more sharply. You could say something decreases twice the rate, but you don't want to do twice that of f of t because you don't want to affect the 17.2. Now, what I wrote before was fine, but that was a makeshift version. I had to really override the concept of what we were doing. Instead, what you want to do is this. Don't double the rate at which the number of sales decrease. Have the amount of time at which sales decrease at the same amount. So you want to do a horizontal stretch instead. You want to say G of t equals F of, if you want to compress time by a factor of 1/2, you put 2t here. That's what gives you the change. I think that's what the book wants you to talk about. You know why? This doesn't affect your y-intercept. You now have -7/5, and then wherever t is gets replaced with 2t, and guess what? That part gets doubled now. So in half the time, you still lose at the same rate. So 6 months into the year, you lose $1.4 billion. So now in the full year, you lose double that, 2.8. So that's what they want to see here. So -14/5 t plus 17.2. So that's the change that you want on that part. How can you transform the graph there? Explain how the sales of 2010 and 2010 are affected by this change. So what you're doing, I suppose what you want to do is look at the difference between f of, not 2010, because 2006 was the year, so f of 4 and g of 4. Let's look at what g of 4 minus f of 4 is, how it changes your difference in sales and overall. All right, so basically like that. So g of 4, I'm writing this all wrong. Let me just write f of 4 equals g of 4 equals, and then do it that way. So f of 4 is -7/5 times 4 plus 17.2, which is -28. I'm going to use my calculator for this. I don't even have it up. I'll just use, not my graphing calculator, but 7/5 times 4 plus 17.2. So that's 11.6. So in 2010, in the original format, there's $11.6 billion in book sales in the year 2010. And then this one, you don't just double 11.6 because remember the 17.2 is a part of the whole thing. So -14/5. -14/5 times 4. That's the part that gets doubled though. -14/5 times 4. All right, so I believe it's going to be, I don't know, I don't want to get it wrong. -14/5 times 4 plus 17.2. Oh, I must not put a negative. Oh, hold on. I totally messed something up. This is why I have to use the actual calculator thing. 14/5, make it negative. There we go. Times 4 plus 17.2. Okay, 6. 6 billion. 6 billion. Okay, so g of 4 minus f of 4 is 6 minus 11.6, which is -5.6 billion in losses or whatever. You know, however you want to put it, right? You get 5.6 billion less made in the new model compared to the old model. So that's how the sales in 2010 are affected by that change. Okay. Numbers 37 and 38. Oh, 37 to 40, excuse me. Numbers 37 to 40 describe the transformation of the graph of f to the graph of g, then find the area of the shaded triangle. Well, because I got to find the area of the triangle, I'm going to go ahead and copy and paste this thing so I can talk about numbers. So I don't know what the shading has to do with it besides that. I think they're just having fun with you in the problem, but let's do it. You know, in chapter 1, we did a lot on area stuff, so it's not totally absurd that we still practice some of it. F is black, G is blue. This looks like a horizontal translation. They just said describe it, so we're not coming up with equations. We're just describing this thing. So we horizontally translate 1, 2, 3, 4, 5, 6 units to the left. So translate 6 left. That's it. If we want to do a full equation thing, okay. They didn't say write the new equation. Sorry, I cut off some of it on the top. You could. It doesn't ask me to. It says find the area of the shaded triangle. I don't think they're asking to do anything particular with stuff. They just said find its area. So it's area, and honestly, the area has nothing to do with like what we're doing on this stuff. So this length here is 6. That's the base. This height can be 3. So the area is 1/2 base times height, which is 9 square units. And that's number 37. Yeah, these questions are kind of weird. They don't really have to do anything with anything. Even to describe the transformations, they don't, you're just translating, it looks like. Oh, no, you're not just doing it on the last two. But number 30, well, you're reflecting on the next two. Number 38 is yet another translation. Number 38's triangle. What is going on? Number 1, number 38's triangle area I think is the same as number 37. Number 2, it doesn't have anything to do with F. So I don't know if the triangle has anything to do with this. All right, F is right here, G is right here. So we translate up 1, 2, 3, 4, 5. So we translate 5 units up. 5 units up. Sorry if it seems a little kind of mundane of what I'm doing here. I don't know what teacher would be assigning these problems really. 2, 3, 4, 5, 6. And it's like, hey, there are some more problems. So 6 units by 3 units. Area is once again 1/2 base times height, which is once again 9 square units. So no change on area there, and has nothing to do with F. Interesting. All right, number 39. Number 39. And the equation is just there for funsies, I suppose. F of x equals negative x plus 4. This is a linear equation. Now, the description I want to make here has to do with reflection, the way that, being a linear equation is flipped over. So with it being flipped over, what axis is it flipped over? The x-axis. So that's the reflection over there from F to G. It's a reflection in the x-axis. So reflect across x-axis. Is that part of the answer? I don't know if I was boxing the other ones, but there's that. Area of the triangle. I'm going to call this the base now. 1, 2, 3, 4, 5, 6, 7, 8. And the height, 1, 2, 3, 4. It's got to be perpendicular to base. So area is 1/2 base times height. Half of 32 is 16 square units. And then number 40. Number 40, we have, allow me to copy and paste. We have 5 more questions after this, which I'm looking forward to wrapping a bow around this one when we get questions like this. All right, number 40. This one reflects across the y-axis. Here's your F, here's your G. So everything's flipping over, this way, like that. So we reflect across the y-axis. Across y-axis. And then, the area has a length of 1, 2, 3, 4, 5. I'm going to guess 10 there. Base length, and a height of 1, 2, 3, 4, 5. So your area of this one is 1/2. Honestly, I thought it was going to be 16 again. Half of 10 times 5, which is 25 square units. Okay, those are the areas of those shaded triangles. I don't see the connection on anything we're doing with areas, but that's okay. All right, number 41, abstract reasoning. The functions f of x equals mx plus b and g of x equals mx plus c represent 2 parallel lines. Indeed, same slope, and I guess b and c are different. Write an expression for the vertical translation of the graph of f to the graph of g. So if we're going from f to g on a translation, that means g is the final. So you truly want to do like a g of, this is part A. Vert translation from f to g means you want to do g minus f. I know that sounds backwards, but that's literally what you do, right? You go from the final minus the initial for that kind of thing. Now, I can literally do that as well. I can do mx plus c minus mx plus b. Here's the thing. The mx's will cancel, right? It's all about the, I'll just even write it here. Distribute the negative mx minus b, and then mx's cancel out there. You're left with c minus b. C minus b. That's the translation, right? That's how much we translate it by. So when it says write an expression for the vertical translation, that's what we do. We vertically translate C minus B units upward, right? If I want to translate from 3 to 5, I go 2 units up. Why? Because 5 minus 3. 5 minus 3 is 2. So translate 5 minus 3 units upward. So C minus B is just a good version of that for part A. Part B, use the definition of slope to write an expression for the horizontal translation of the graph of f to the graph of g. Okay, so because the slopes are the same, we're doing a rise of C minus B, therefore we can do a run. Well, the slope isn't necessarily 1. The rise is m times bigger. So if you're doing, hold on, if a slope is change in y over change in x, and if one of the changes you can make is doing a rise, I need to think about that with actual numbers. If the slope was 3/2, actually, let's see. If both slopes were 2 and one was 3 bigger than it with a slope of 2, so that's up 3, but I have to go up 2 over 1 for a slope, up 2 over 1. Let's see what I'm thinking about with that. Then it's 2 times bigger on the rise than it is on the run. So I'm multiplying something by m to get C minus B. So I'm multiplying something by m to get C minus B. So if my delta y was a C minus B, I guess I can just do that. You multiply both top and bottom by some delta x, and delta x times m equals C minus B. So delta x equals C minus B over m, I suppose is what you do there. You take your rise and you divide by the slope to get how much you'd run. Use a definition of slope to write an expression for the horizontal translation of the graph of f to g. I believe that's it for the horizontal translation. You go that many units in that direction. That's what I feel. I don't know. I think that's good. Yeah. If you rise that much and you run that much, it maintains that slope. Yeah, sounds good. All right. I don't know if that's how they want to express it. They never said in terms of slope. They said use the definition of slope. So I'm going for it. All right, number 42. How do you see it? Consider the graph of f of x equals mx plus b. Describe the effect each transformation has on the slope of the line and the intercepts of the graph. If you reflect the graph of f in the y-axis, so if you reflect it in the y-axis, it's going to now be like that. It's going to be this way. So how does it affect the slope on A if you reflect y-axis? The slope changes sign. The y-intercept is the same. X-intercept changes sign. They said intercepts. So x-intercept turns positive, slope turns negative, y-intercept is unchanged. That is part A. Part B. If you shrink the graph by a factor of 1/3, if you shrink the graph vertically by a factor of 1/3, what's going to happen is the x-intercept is going to stay the same while everything else becomes a third of what it is. It's going to look like that. Okay, so the slope becomes a third of what it was. The y-intercept becomes a third of what it was. So shrink graph vertically. So vertical compression factor of 1/3 means the slope will be 1/3 smaller. You divide it by 3. Y-intercept 1/3 smaller. I like this question. X-intercept is same. Part C. Stretch the graph of f horizontally by a factor of 2. Well, when x is 0, that height's going to stay the same. And then this has to stretch twice as far out. So this would be like going out here. So now this graph would look, like that. Everything's horizontally stretched like that. So this is an example of why a horizontal stretch is the same as a vertical compression, right? So horizontal stretch factor of 2 means your slope is now half smaller, right? The slope is the rise over run. There's less rise for the amount of run, or more run for the same amount of rise. Y-intercept is the same. X-intercept is doubled. 2 times bigger. Right? It's doubled whatever it was. All right, that is how I see it. All right, 3 more questions. Number 43, reasoning. A lot of words in these next few. The graph of g of x equals negative 4 times absolute value of x plus 2 is a reflection. It is a reflection in the x-axis. Vertical stretch by a factor of 4 in translation 2 units down on the graph of its parent function. Agreed. Choose the correct order for the transformations of the graph of the parent function to obtain the graph of g. Explain your reasoning. I think they said it. Choose the correct order of the transformations of the graph of the parent function to obtain the graph of g. They have it. They already have it. So I always like to go left to right. This, then that, that kind of thing. I like to do any of the stretches and reflections first. I'm confused. I'm going to pause and think about it just in case there's something I'm not reading right. Okay, there's something I didn't read right. This was a +2, and here they said translation 2 units down. So there's something that needs to swap, and I think it's the reflection that needs to go last. As far as the vertical stretch should still go before the translation, otherwise this would either say a 1/2 or this would have to be an 8 to make it 4 times bigger. So it looks like the vertical stretch would still have to go first. So you are still doing a vertical stretch first, and then you're doing the translation. But then I think you do the reflection after. And the reason for this is because reflection has to come after the translation in order to change that 2 units down into a +2. If we translate, did they say explain? Yeah, if we translate 2 units down, but the equation has a +2, then the reflection needs to occur after the translation to officially go 2 units up. Okay, I didn't see the +2 there, so now I do. So what you're really doing here is you're taking your g of x, you want to vertically stretch by a factor of 4 to your function. You want to go 2 units down, but in order for it to say a +2, this needs to now reflect over, and that all needs to be negative. That's what gives you negative 4 times f of x plus 2 like that, and f of x, of course, is absolute value of x. So g of x is negative 4 times absolute value of x plus 2. Actually, they never said f of x. I probably should have just said that the whole time. So let me just make it that. And sorry, kind of winding down here. Absolute value of x, absolute value of x. Okay, so that's where the +2 comes from. Awesome. Now I got it. I was really confused for a moment. I'm like, they're not just going to tell me the same thing, right? All right, number 44. You are planning a cross-country bicycle trip of 4,320 miles. Your distance d in miles from the halfway point, sounds like an absolute value thing, can be modeled, can be modeled by d equals 72 times absolute value of x minus 30, where x is the time in days and x equals 0 represents June 1st. It's my mom's birthday. Your plans are altered so that the model is now a right shift of the original model. Give an example of how this can happen. Sketch both the original model and shifted model. Well, I'm hearing sketch, so I'm automatically thinking, let's start with a sketch and see what we can comprehend in the problem itself. Now, with respect to the absolute value aspect of this problem, hold on, I'm getting it set to go. With respect to the nature of the absolute value portion of this problem, and I don't know what we're supposed to understand or not, but as far as vertex form goes, d equals 72 times absolute value of x minus 30. X minus 30, we go 30 to the right for the vertex. 30 is like whatever here. And then this has a slope of 72, whatever that's supposed to mean here in a bit. I'm going to look at all that in a second. I kind of was just reading the problem and not comprehending it at some point. So let's see what they're saying with this model. They said something about shifting it to the right, right? All right, let's say we have that. You're planning a cross-country bicycle trip of 4,320 miles. Your distance from the halfway point can be modeled by this. Your distance from the halfway point can be modeled by this. X is, so distance in miles from the halfway point. So, I see. So, you travel 4,320 miles. You want, maybe they shouldn't have arrows. The halfway point is so that you do half of that travel. I mean, I don't know if they accounted for it in our model, but you do half of the travel, half of 4,320 this way, and then half of 4,320 back. It says your plans are altered, so the model is now a right shift of the original model. Give an example of how this can happen. I don't know. I'm really confused. I mean, well, actually, this thing probably already accounts for that whole halfway point biz. Let me see what 72 times 30. Let me see if 72 times 30 is half of 4,320. 72 times 30 is 2160. That's half of 4,320. So, okay, so that already accounted for that. Your plans are altered, so the model is now a right shift to the original model. So here's the original model. Let's alter the plans so we have a right shift. So let's shift it to the right. Like that. Whatever, right? They didn't say anything about horizontal translation or compression or anything like that. They just said, yeah, horizontal translation. Give an example how this can happen. You don't start on June 1st. X equals 0 represents June 1st. A shift. Okay. I thought they were talking about something else. A right shift can happen if you don't start your cross-country, I don't know if this is right, bicycle trip on June 1st, but instead on a later date. I don't know. That's just weird. Sketch both the original and the shifted. Okay, I did it. I don't know if that's what they meant, but that's what I'm going with. That just, yeah. Kind of confused on the problem. I apologize if I didn't understand it. These problems at the end get a little like, what are you talking about? Okay, and the last question is number 45. Let's go. Use the correct value, 0, -2, or 1, with A, B, and C, so the graph of g of x is a reflection of the x-axis followed by a translation 1 unit to the left up and 1 unit to the left and 1 unit up of the graph of f of x. Explain your reason. Okay, here's what I'm going to do. I'm going to take the f of x equation. I'm going to translate, I'm going to reflect, I'm going to reflect across x-axis. Let's start with that. So I'll call this h of x. H of x takes your f of x and reflects across x-axis, so it makes it negative. So we're going to have -2 times x of x minus 2, and then minus 1. Changes everything. Now we're going to translate 1 unit left. I'll literally just do them piece by piece. So this will be called k of x. I don't know. I think I skipped the letter j. I also skipped I, but generally we don't use that vowel. K of x is going to take your f of x equation and add 1 to it. So this will be negative 2 times absolute value of x plus 1, and then minus 2. So 1 minus 2 is negative 1. Minus 1. Now we're going to translate 1 unit up. 1 up. And this will be, I'll call this one j of x because I skipped it. So that's f of x and then plus 1. Oh, sorry. I can call this one g of x now. Huh. So g of x is the final one. So g of x is taking this negative 2 times x minus 1 in the absolute value, and then minus 1 plus 1. Negative 1 plus 1 is 0, so you have g of x equals negative 2 times the absolute value of x minus 1. So there's my final result. They said take the numbers 0, negative 2, or 1 in the g of x equals a times absolute value of x minus b plus c. That would mean that a is negative 2, b is 1, and c is 0 for that guy. All right. The math was the explanation for it. All right, guys, that's the last problem, and that'll do it for this one, right at the 2-hour mark about. This is Mr. Robinson. Thank you so much for watching. Sorry about that number 44. It got kind of screwy. I hope I did it right. But y'all, wasn't really much on graphing. I expected the 2.2 and 2.5 to be explanations of how to use like vertex form and graph them, but it sounds like it's not something they're really intent on doing. So just keep in mind, whenever I graph, I'm going to use things without a table when we do them. So thank you so much for watching here. Next up will be section 2.3. Take care. See you in the next one. Bye.